Yes, now let's look at how the gradient descents applied to linear regression models look like. I think it's a quite straightforward application because everything is well defined in linear regression. We have the form for the cost function in linear regression, right? Like this. It is the mean square error function. It is a summation of the difference between yi and the prediction on data xi raised to the power of 2, sum up everything, divided by 2 times n, right? And the gradient descent, we need to use gradient descent, we need to start with some initial values. For example, we have started from theta 0 and the theta 1 all equal to 0, okay? And we update the parameters using gradients, okay? And we stop with some certain conditions satisfied. So the cost function is this. If we take the derivative of it with respect to theta 0, right? So the first step here, we simply rewrite the function, right? And here, when we take the derivative of with respect to theta 0, oops, we consider everything else as constants, right? And nope, sorry, that's not correct because there's a 2 here. So we need to move the 2 outside, right? We outside the exponent and decrease the 2 by 1. That is rule of taking derivatives. And within the function inside, the constants, the coefficient before theta 0 is 1. Okay, so that's what's left within the function, within the derivative in this form, right? And for theta 1, we have additional constant here. So we need to take it out here, right? That's the rule of computing derivatives. So in the assignments for the task 2 and task 3, we need to implement the 2 gradients with NumPy, okay? And the form of the gradients, they are these 2 equations. So it is a summation of, so this one is easier to implement, I think. So it's a summation of a bunch of differences. So we can, if the y hats and the y's, they are all in vectors, the NumPy would let you, can allow you to minus 2, subtract 1 vector from the other by simply using the vectorized operation. And you can call the summation functions to sum up all the values. And to this one, the gradients with respect to theta 1 is a bit tricky because it is the summation of a bunch of products. Okay, so this is a typical form of inner product or dot product. Okay, so basically you want to you will need to call the built-in functions in NumPy that conduct the dot product. I think we will have more hints later on in later slides. So anyway, that is the forms of gradients for linear regression models. So with these forms, we can plug in into the formula, right? We can plug in into the formula of gradient descent. We use them to update the parameters theta 0, right? Theta 0 and theta 1. So here I neglect the superscript. After the updates, the theta 0 will be of different values, and so is the theta 1. Okay, and we need to update theta 0 and theta 1 simultaneously. Okay, that means if we want to implement with programming languages, we want to use some temporary variables to store the intermediate results, because after the theta 1 is computed, if the after theta 0 is computed, if that values of theta 0 is changed, it becomes risky, because if we want to rely on theta 0 when we compute theta 1, that will be a problem. Okay, so we need to basically do the simultaneous updates. Okay.
Professor, I have a question. So until the page, the last slide, that it seems like everything is exactly the same as normal equation, but from this page and later on, that everything is kind of like update to the theta 0 and theta 1. Can we regard kind of like the gradient descent is a numerical method of solving the matrix solution?
That's a good thought, I think. So, what the software packages like NumPy does for us in computing the inverse of a matrix must utilize some numerical methods. And I don't know what detailed methods they are using, but must be some numerical methods. But for the gradient method, I think gradient method is kind of the numerical methods that can be used to solve the inverse of a matrix.
Okay, thank you.
Yeah, I think it's a reasonable thought. Yes. And the advantage of gradient descent is that the goal is clear. We have a very clear goal that we want to minimize the cost function. So the numerical values computed in each iteration, they are meaningful. They are the amount of values that we want to tune our parameters. Okay, we want to tune the parameters so that the cost function becomes smaller and smaller. Okay, and we can control this step by setting up the alphas, by setting up the learning rates. If we want to learn faster, we set larger alphas, but that becomes risky. If we maybe we will miss the minimal points or something, and I will cover that issues in a later topic, in the later slides here. So, and that's for simple linear regression. Okay, and for multiple linear regression, we have multiple variables, multiple parameters. So it'll be easier to handle this with matrices. So here's the form of the cost function for multiple regressions. We have n+1 features, including theta 0 to theta n. Okay, so the gradients we want to compute with respect to the parameters becomes a long vector. It's not just theta 0 and theta 1. We need to compute the gradients for theta 0, for theta 1, theta 2, and theta n, right? And actually the form is also quite easy to memorize. It is just the difference. You see the difference between the predicted value and the actual value times that feature, right? That is the gradients for theta 1. And for the gradients for theta 2, it is a difference times the feature for that, times the feature in that, that correspond to that parameter, okay? And sums up all across all the data instances. And it is quite easy to memorize, and it also eventually is can be implemented in a matrix dot product style. So to put it short, it is just this way. Okay. So these are the gradients, and the next step is no difference from the case for simple linear regressions. We basically updates the parameters simultaneously. Okay, so it's a bit like tuning process. Okay, so for example, if we observe the forms of the gradients here, right? We'll see that the magnitude of the gradients, they basically depends on two parts. So the first part is how different the predicted value is from the actual value. That's the difference. And the second part is the feature part, and that feature is kind of a weight to that parameter. So larger features put larger weights to that parameter. Okay, so if x2 has a bigger value, then the corresponding gradients with respect to θ2 also tend to have a relatively larger gradients. So it's a kind of a very carefully designed negative feedback system. Like if that feature contributes more to the bias between the predicted value and the actual value, then the amounts of change that parameter needs to make is also relatively larger. Okay, so it's kind of a tuning the equalizer. It's kind of like this system. When one channel or one feature makes larger contributes to the outputs, then it also needs to make larger changes in order to make the system fit the data well. Okay. So that's pretty much of it for the gradient descent methods for simple linear and multiple linear regression models.